Welcome to this explainer. Today, we're talking about something pretty wild, the invisible software that secretly powers our entire physical world. I mean, think about it. Every single time you start your car, use the office printer, or rely on a medical monitor at the hospital, there's a hidden blueprint completely running the show behind the scenes. Okay, let's dive into this because the stakes here are actually incredibly high. Have you ever wondered how a life-saving medical device knows exactly when to trigger without even a split second of delay? If your standard desktop computer freezes, right, you just reboot it. Maybe you lose an email, no big deal. But if a pacemaker or your car's anti-lock braking system freezes, the consequences there are literally life or death. The difference between a tiny glitch and a total catastrophe lies entirely in its firmware architecture. So what exactly is this invisible software? Well, firmware is basically a small piece of code that lives right inside a device's non-volatile memory. It's the hidden engine inside everything, from the voice-over IP phone on your desk to your car's brakes. And it's distinctly different from a normal operating system. See, firmware handles the really low-level heavy lifting. It loads and manages the bare metal hardware and the OS itself, whereas the operating system's job is just to carry out your actual user tasks, like, printing a document. And that brings us to a really sharp contrast in how modern systems are actually designed. On your desktop PC or your phone, you're likely running what's called a general-purpose operating system, or GPOS. It's fantastic for dynamic apps and user software. But embedded devices, they demand something completely different. They need predictable, absolutely timely responses. And that is exactly where a real-time operating system, or RTOS, steps in. It provides the incredibly precise, deterministic scheduling of the CPU and memory that these embedded devices absolutely require to function safely.
Section 1, the language of firmware, building blocks. Before we get into the heavy architectural paradigms used to structure these systems, we really need to understand the raw materials. The engineers writing this code are operating under extreme hardware and memory constraints, stuff that regular app developers honestly never even have to worry about.
To build these systems, developers basically choose between two main paths, assembly language and high-level languages. Assembly is super low-level, system-related programming using processor-specific mnemonics. It gives you insanely efficient memory usage and blistering performance, but it's not portable at all, and it takes a really long time to write. On the flip side, high-level languages like C and C++ drastically speed up development, and you can port them across different devices, though they do rely heavily on cross-compilers to translate the code properly.
And this brilliantly illustrates how human-readable code actually becomes machine action. We're looking at the translation pipeline here. First, an assembler takes your source file and translates it into an object file. Then a linker or locator steps in and pieces together all these different object modules into one absolute hex file. That final hex file is the raw binary machine code, literally just pure ones and zeros, that gets dumped straight into the processor's memory to bring the device to life.
Section 2, the superloop, simplicity first. Now that we have our raw code, how do we organize it? Think of this specific approach like a relentless, unstopping assembly line worker. One who just goes down the line, performing tasks one by one, forever. The flow here is incredibly rigid, very sequential. First, the system configures its common parameters and initializes the hardware components. Then, it starts the first task, executes the second, marches all the way down to the last defined task, and finally, jumps right back to the very first task to do the whole thing over again. It's a continuous, infinite loop.
Now, what's really interesting about this slide is how it shows the only way to actually break out of this infinite loop: a hardware interrupt. If an interrupt happens, the routine hits pause, temporarily suspends the current task, handles whatever the interrupt was, and then drops right back to the exact point where it left off to keep the loop going. But there are major real-world trade-offs to this kind of simplicity. Superloops are incredibly cheap and simple to implement, which makes them absolutely perfect for inexpensive electronic toys, simple monitors, or basic card readers. But they severely lack real timeliness. Because tasks execute cooperatively, one after the other, there's no preemption. So if a single failure happens in one part of the loop, or one task hangs up, it takes down the entire system. Section 3. The layered approach, separation of concerns. Let's move on and see how this builds up when a superloop just isn't enough. This layered approach creates clear boundaries and is actually the architecture that heavily dominates modern automotive and medical devices today. Let's break these layers down using a quick analogy. At the very bottom, you have the hardware abstraction layer, or HAO. Think of the HAO as a universal translator. It isolates all the messy hardware-specific code. Right above that, device drivers control the actual hardware but expose simplified interfaces. Next up, middleware provides common services like your communication protocols. And finally, sitting at the top, the application layer handles your core business logic. This clear separation of concerns is a massive deal because it means you can swap out or upgrade the underlying hardware without having to scrap and rewrite your entire application.
Section 4. RTOS and package-based designs. But what happens when strict split-second timing and massive scalability aren't just nice-to-haves but absolute necessities? We shift our focus to these more advanced architectures.
For highly critical applications, an RTOS brings some incredible, totally non-negotiable features to the table. Preemptive scheduling means high-priority tasks can literally interrupt lower-priority ones to make absolutely sure deadlines are met. Deterministic timing guarantees predictable response times, which, by the way, is absolutely crucial if you want to pass safety certifications. Add in standardized inter-task communication and robust resource management to prevent system deadlocks, and you've got an incredibly reliable foundation.
Alternatively, if you need to manage massively diverse product variants, you'd look at a package-based architecture. This relies heavily on compile-time configurations, runtime feature detection, and modular plugins. Basically, it lets development teams adapt and scale a single unified codebase across multiple evolving product lines really efficiently. So instead of rewriting the firmware from scratch for every single new device model, engineers just plug in the specific modules they need. It's kind of like Lego for firmware.
Section 5. Making the right choice, the ultimate trade-off. So the crucial point here is how development teams actually select one of these blueprints in the real world. It's all about balancing strict hardware constraints against intense real-world demands.
Let's ground all this technical jargon back in a very harsh reality for a second. What happens when a deterministic scheduling failure means an autonomous vehicle doesn't hit its brakes fast enough? In the smartphone app world, bad architecture just means a sluggish, annoying interface. But in the embedded systems world, bad architecture bricks expensive devices. And in safety-critical sectors, a well-chosen architecture literally saves lives.
Let's summarize the Big Four paradigms side by side to put this in perspective. The Superloop needs very few resources, making it ideal for simple, cheap devices. The layered approach demands moderate to high resources, but it's perfect for complex products that are going to be in the market for a long time. RTOS demands even higher resources to guarantee that life-saving preemptive real-time performance. And finally, the package-based approach has variable resource needs, but it is the undisputed champion for managing huge, multivariant families of products.
Ultimately, it's the real-world constraints that dictate the final architectural choice. If your device has high safety criticality, boom, you're immediately looking at an RTOS or a layered architecture. If your team is small and hardware diversity is low, honestly, a Superloop might actually be the smartest, fastest route to market. Every single factor, from your memory budgets to how you plan to do field updates, all the way to strict industry certification standards, steers the engineering team toward a very specific paradigm. The research across all our sources overwhelmingly supports this one key idea. Architectural decisions made early in the development process yield the greatest benefits in terms of reduced maintenance costs, improved quality, and enhanced scalability. Investing the time and money to choose the exact right software foundation on day one guarantees long-term product viability, significantly lowers defect rates, and above all, ensures the device is actually safe to use.
It really makes you look at the world differently, doesn't it? As embedded systems become increasingly complex, I want to leave you with this final thought. What invisible architectural blueprints are secretly running the physical devices you interact with every single day? The next time you tap a card reader, start your car, or rely on a medical device, just take a second to think about the unseen, meticulously chosen code making it all happen perfectly. Thanks so much for joining me for this explainer, and keep exploring the hidden systems all around you.